Hey everyone, I hope you all are safe and doing good. So we have discussed all the simple type of sorting algorithm, bubble, selection, insertion. Now let's see some efficient sorting, quick, merge, heap. Heap already we have seen. So let's see what is quick sorting and we'll see how it works and why this one is good. We will analyze this also time and space complexity. Now suppose two arrays are given to you. And if I quickly ask that from this array, after sorting this array in ascending order, what is the correct position? What would be the correct position for this element 60? You can quickly say that 60 is the largest, so this is the correct position for 60. Even after sorting, 60 would be here only. Yes? Okay. From this array, if I ask, what after sorting this array, what is the correct position for suppose 20? So even after sorting, if I sort this, so the array would be 1, 5, 10, 20, 40, and 25 and 40. The correct position of 20 would be at third index only. Yes? So it's already at the sorted position. Have you come to know that it's already at the sorted position? If you think a little bit, then see, all the elements to the left of this are less than 20. All the elements in right of 20 are greater than 20. So one thing is for sure, this 20 is at its correct sorted position. It doesn't matter all the left elements are sorted or not, all the right elements are sorted or not. But one thing is for sure, all the right elements are greater than this, all the left elements are less than this. So 20 is standing at its correct position. He said that I am standing at my correct position. I don't know about the remaining students or the remaining elements. Okay. So this kind of you can say logic we will apply for quick sorting. What we'll do is, so let's take this array itself. This array itself. So what are the steps in quick sorting? First thing, we select the pivot element. Any element you can select. It's like, suppose I'll select from this array. Let's suppose this array. I'll select at first 10. Suppose 10. Now you have to find out, you have to place it at its correct position first in this array. I'll select 10, I'll place it at the correct position. So what is the correct position? Have to find, that is a logic that we write. But suppose from now we know that the sorted array would be 1, 5, 10, 20, 40 and 25. So I know that the correct position of 10 is this 0, 1, 2, 3, 4, 5 at second index. So I'll place this here. Now let's pick 1. What is the correct position for 1? Here. Place it here. Pick 5. What is the correct position for 5? After sorting. Here. Put it here. Pick 20. What is the correct position for 20? Here itself. What is the correct position for 40? Here. What is the correct position for 25? Here. And now see, there is sorted. 1, 5, 10, 20, 25 and 40. So that is overall like the basic idea. Pivot element is, we select any element as a pivot element. We find out the correct position for that element and we place it there. Now here you can easily tell the correct position of 10 is here, because you can easily see that we have sorted array and 10 is here, so that's why it's here. But in code, how you will write down this thing, that is really important. Okay, that is the main idea behind this. So very first we will select a pivot element, any element. Now what is the pivot element? It can be first element like this, first, or last element. Last element also you can consider, or median element you can find out and consider that, or any random element, any random. It's up to you. Sometimes the performance also depends on the selection of pivot element. It depends. Okay. But for now, just to make you understand what is the working of quicksort, I will assume that always the first element as pivot element. Somewhere you find out that they consider last element as pivot element. Somewhere median element, somewhere random element, somewhere like any other element or middle element, something like this. Okay. But we will consider first element as pivot element and then find out the correct position for this, that element and place it there. So first step is simple. You have to select the pivot element. That is the first one. Now you have to place it at right position in the array. in sorted array, in sorted. Once the array becomes sorted, what is the correct position for 10? This, so just place it there. Have to find out this correct position. That is the main thing. That is the main thing, right? So mainly we will do what, have to find out now this correct position. What we will do is, see, let me just rub this and we'll consider one good example for this. So we have suppose this array and now you have to sort it in ascending order. That is your assignment. That is your task, and we will use quick sort. So how quick sort works? At first step is select a pivot element. So first, now see, whatever array we have, let's assume here we have, this is my low and this is my high. Or let's say for first we don't have any low or high. I'll tell you why we take 2 pointer here. At first what I'll do is I'll consider this 6. So at first my pivot element is 6. Whatever first element in right now in my array, from here to here, because I have to sort, 6 is my pivot element. You can say ARR of 0th, this element. Yes. Now you have to find out correct position for this 6. How we will find out? See, we know that we place 6 somewhere, that this is my 6, or you can say this is my pivot element. It's like all the elements here is less than pivot, all the elements here are right, are greater than pivot. So it's like we can say we have divided this array into two partition. This is partition 1, partition 2. Here the values are, all the values are less than pivot, values are greater than pivot. Okay, that is fine. But what about if values are equal to this? If suppose I have one more 6 here, which side you will put, this or put this or this? It depends on you how you apply the logic. But I'll prefer that I'll place all the values less than and equal to pivot this side and greater than pivot at this side. So it's up to you. Maybe you can say all the values less than should be this side, all the values greater than and equal to this pivot element should be at the right side. It's up to you, right? Any way you can write down this thing, right? So this is how we do. So basically what we are doing, we are partitioning this array into some sub arrays. This is one sub array, this is second sub array, something like this. So this partitioning, this step is really crucial in quick sort. So basically we are dividing, so that's why it's a divide and conquer sort. It follow the process or the approach divide and conquer. We divide and then we find out the correct position, right? How we will divide, how to find out the correct position? Let's see. So here what we can do is we have to find out the smaller values from this and greater values from this. It doesn't matter all the smaller values are sorted or not, greater values are sorted or not, but we just have to find out the correct position. Smaller values as well as greater values. So what I can do is, better approach is, let's take 2 pointer. 1 pointer will start from here. Let's take I. 1 pointer will start from here, J. Yes. So here we are using 2 pointer approach to solve this question. This one was low, this is high. Low high means the lower bound and upper bound of the array on which I am working. Because after dividing this in two parts, this is my pivot element and this is my first partition, this is my second partition. So what I'll do is, again I'll apply the same process, if you get the idea, on this part and on this part recursively. So at this time the array would be from here to here, from 0 to some point. At this time the array would be from here to high. So we need these boundaries, low and high, lower bound and upper bound. That's why I'm just taking low and high. Yes, we need to tell on which, at which boundaries low and high we are applying the partition or we are applying the quick sort. Yes. So what is the actual process? See, I'll take i's here, I'll move I and I'll move j this side. Yes. have to move. So at first, see, my I is 0 and my pivot is also at 0th index, so it's 6. At 0th index, I have 6. Now I'll check at first. See, I want that 6 should be somewhere here. Smaller values will be at this side. Larger value should be at this side. So what you have to do is, if there is any greater value than the 6, we will move at this side, at that partition. And in this partition, if right now in unsorted array, if there is some smaller value than this or smaller or equal value, we bring that value this side. Something like this we have to do. Yes? I hope you are getting my point. So we start comparing from here only. So we compare. If the value at this side, if the value is less or equal, it's okay, we keep going. Because that's exactly we want. The value at this side should be less or equal. So the 6 is less than or equal to 6. Yes. Yes. So we keep going. So we just do I plus plus. So we just increase this I here. Now I becomes 1. Now let's see. I1. At I1 I have 7. Again check. Is 7 less than equal to 6? 7 less than equal to 6? No, it's greater. So this should be at the end portion. I don't know where, but it should be at the end. No, it's not equal. Stop. So just stop. I is here. Now check for J. J is right now 7. Index is 7 because size is 8. At 7 I have 2. So when we will move the side, if the elements are greater than 6, then we keep moving. Once you get the element less than this, stop, because you have to bring that element this side. So compare this element 2. If it is greater than 6, greater than the pivot element, then we just do j minus minus, j minus minus. We keep moving. Is it true? Is this 2 greater than 6? No. So as soon as you get the first element which is less than pivot element, stop there. Stop. So my j is here itself. Now what you have to do? Now I got, this is the, when we are moving from this to this is the first large element, then pivot element. This is the first smaller element, then pivot element. So we swap these two. We swap I and j. Yes. So now we swap this with this. So 2 would be here and 7 would be here. Yes. But don't stop. Now again, keep going this side and this side. When to stop? I'll show you when to stop. Because there are still many elements left. You have to check all the elements. Right. Now, we have swapped this with this. Now again check. Again start. I is equal to 1. At 1 I have 2 now. At 1 I have 2. Check. Is this 2? If this 2 is less than equal to pivot element, then we keep going. Is this less than equal to 6? Yes. Then keep going. Keep going means do I plus plus. Now I becomes 2. So now my I is here. I is equal to 2. Check. I is equal to 2. I is equal to 2. So that is at I have 70. Is 70 less than equal to 6? No. Stop. Stop. I is here. Stop. First greater element again I got which is greater than pivot element. Now start with j. Again. J is equal to again 7. Still 7. At 7 I have 7. Is 7 greater than 6? Yes. Keep moving. Yes. So we just do j minus minus. So j becomes 6 because I want greater element this side. Now j is equal to 6. At 6th we have 45. Is 45 greater than 6? Yes. Then again j minus minus. So j becomes, j was here first, is still greater. So again move, j is here. Now j is 5. At j5 we have 90. Is 90 greater than 6? Yes. Again move j minus minus. So j becomes 4. So now j is here. Now j is at fourth index. At 4 I have 2. Is 2 greater than 6? No. This is the first element now you get at this time, which is less than 6. So stop. Now j is here. J is here. Now what we do? Same swap. Swap this with this. So here we have again 2. Here we have 70. Yes. But we still not stop. We again check because still we have one more element, few more elements left. When to stop, I'll tell you. Now again check. Now I is equal to same. I is 2. I is 2. At 2 I have now 2. Element is 2 after swapping. So is my 2 less than equal to 6? Yes. Keep moving. I plus plus. I becomes 3. So now I is here. I is here. At I is equal to 3. At 3 I have 3. 3 less than equal to 6. Yes. Again move. I is equal to 4. Now I is here. Yes. Now check. At I4 what we have? Now 70. The element is 70. Is 70 less than equal to 6? No. Stop. This is greater than 6. So it should move to the right side. So stop here. Stop here. I is here. Now check with J. J is also 4. At 4 I have 70. Is 70 greater than 6? Yes. While moving from this to this, we check. If element is greater, keep moving this side. Yes, it's greater. Keep moving this side means J minus minus. So now J is here. I is here, J is here. J is equal to 3. We have element is also 3. Is 3 greater than 6? No. Stop. Stop. Now I is here, J is here. Do you need to swap now? No. Why? Because we have crossed. I has crossed J means we have checked all the elements. So now don't swap again. Stop. No need to swap. Yes. Now we got the correct position for my pivot element. And what is the correct position? Whatever this jth index. This is the correct position right now for your 6, for your pivot element. Now we swap because I is not less than j. So we stop that loop, one iteration of the loop. Now we swap 6 with 3. Pivot with whatever at jth index we have. So we swap here we have 3. Here we have 6. Now see the array becomes something like this. Now previously this was my array. Now my array becomes after swapping. Let me just change it. So it becomes 3. Here we have 2, 2, 6, 70, 90, 45 and 7. This is my array now. This was my pivot element. So we got my, you can say, partition 1 and partition 2. So it's like we can say partition index or the position or location, whatever you say, whatever variable name you take, you can take. Now this 6 is at its correct position in the sorted array. All the elements in the left side are less than 6. All the elements in the right side are greater than 6. We don't say that these elements are sorted, these elements are sorted. But 6 is at correct position. After even sorting, you will get 6 here itself. So one element we have sorted. One element we have put at its correct position. Now we have partitioned this array into 2 parts. This is partition 1, partition 2. Now apply same process for this and this recursively. Okay. Now for partition 1, if I apply again recursively quick sort for this. So I have an array now 3, 2 and 2. Obviously I'll apply on this only because 6 is already sorted now. So here I have my low and here I have my high. The bound, lower bound, upper bound for this is this only. For this, it's from here to here. So you can say for this, the lower bound is as it is, low only, but high is whatever the partition index you get minus 1. Partition index minus 1, that is my high. For this partition, I'll pass when I recursively call the quick sort. The low is partition index, whatever you get plus 1, and high is as it is, whatever the high is. That's it. So let me just quickly do this for this only. I'll not write in this for everything. You just do yourself. But first, let's go for this again. So now I'll again select pivot element for this. The first element, that is 3. And at first, now my I is 1. Sorry, I is here, J is here. So I is 0. At 0th index, I have element is 3. Now we know that element is 3, pivot is also 3. So we check from this side. Is 3 less than equal to 3? Yes. So we do I plus plus. Now I is here. I is here. Now I is equal to 1. At 1 I have 2. Is 2 less than equal to 3? Yes. So again I plus plus. Now I is here. Now see, I'll tell you. I is equal to now 2. At 2 I have 2. Is the element 2 less than equal to 3? Yes. Again I plus plus. Now where I will go? There is nothing. It's outside of this high. So stop now. Stop. Now no need to check. Now you have to put two conditions also in this while loop. Once this I, if the I is less than or equal to high, then only we move. As well as second condition is when the data is less than equal to pivot element, then two conditions are there to move in forward direction, to do I plus plus. Yes, I hope you got it. Now we are out. It's greater than equal to high, so stop now. No need to do further move. Now my I becomes what? I is equal to 3 because it was 2, so it becomes now 3. Index is 0, 1, 2. I is 3. Stop now. We don't compare. Now check for J. J is equal to right now 0, 1, 2. It's 2. At 2 we have element 2. We check if element is greater, then we move this side. So if 2 greater than 3, no. So stop. Stop there. J is here. So J is now 2 and I is 3. Do you need to swap? No need to swap because I is greater than J, so it has crossed J, so no need to swap. Now, yes, you need to swap. Now, you got the correct position for pivot element, that is whatever at J. That is the correct position. Now, we swap with pivot element with this. So, after swapping, this becomes, array becomes, we swap this with this. So, 2 is here, 2 is here, 3 is here. This was the correct position for 3 right now for this array. So now we divided this into two parts. This is the first partition, this is the next partition, but in right partition there is no element. So we just apply quick sort again for this and this only. So let's try to apply this because generally students get confused when we have 2, 3 or small elements. How to apply a quick sort. Let me just do this for because we will again apply quick sort. But now my partition is only 2 and 2. That's it. So 0 and 1. My low is this, high is this. And say my I is this, J is this. Right now my pivot element is 2, the first element, that is 2. Again check. I is 0. I is equal to 0, element is 2. Is 2 less than equal to pivot element? Yes. So we do I plus plus. So I is here. Now I becomes 1. At 1 also we have 2. Is less than equal to 2? Yes. Again I plus plus. So I becomes, now I becomes what? Here. Pointing to here, that is 2. So I is equal to 2, but it's greater than high, so stop. Now go for J. J is equal to first, sorry, 1. At 1 I have 2. Is 2 greater than, is this greater than whatever pivot element 2? No, it's not greater. So stop, stop. So J is here only. But do you need to swap I with J? No, because I is greater. They have crossed, so no need to swap. Now we got the correct position for the pivot element. Pivot element is 2. Jth, at jth index, J is still here. J is equal to 1 and I is equal to 2. So whatever at jth index, we swap this with 2. So obviously same element. So it's like we can say we swap this 2 with 2 is here, this 2 would be here. So after swapping, the array is 2 and 2. This was my pivot element 2. Now again we have partitioned this array into two parts. One is this partition, one is this. This is partition index. But on right side again there is nothing. We have only left partition. There is only one element. Only one element. Now see how things are working. Only one element. If you apply quick sort again on this partition, so low is high, low is this, and high is also this. For this partition, low is also this, high is also this. If low and high both are equal, do you need to do any sorting kind of thing? No, because there is only one element. So when low is less than high, then only we uh, do these kind of process. Now, is low less than high? No, it's equal. Stop. Recursively, we'll go back, right? Then this is done. This right is done. Now this is done. Okay, sorted. We have 2, 2, and I guess 3. This part is sorted. Now just apply same quick sort for the right part. I guess you can easily try run this. So you do yourself. Don't stop here. Do yourself and see it's working or not. So we have already sorted this like 2, 2, 3. We have 6. Now just have to sort this partition. Apply same process here. Have to write down. If you want to write down pseudo-code, have to write down. See, I'll call like quick sort. There I'll pass what? Array. Array and low and high. Yes. Low is 0 at first, high is whatever array length minus 1, that is high. That we pass. Yes, right? So we have called this. Now let's just define this method. So we define quick sort and we just accept like int array, int low and int high. Now what we do in quick sort? What we do is we partition. First thing what we do is we partition. Then we again apply quick sort for this partition, this partition. So 3 things we need to do. Partition and get the partition index and then recursively call for left and right partition. Quick sort again. Okay. But so see basically what we do here if I write. So let's call a method named partition. I'll define that method that will give you the partition index. So I'll call the method partition. I'll pass my array. I'll pass whatever the low and whatever the high. This method will return me a index. So I'll just store this any like position or location or partition index, any name you can take, position suppose or index. I just store this. Now after partitioning, what we do? We again recursively call what? Quick sort for first left then right. So for left just pass array. Low would be as it is. But for left partition, high is whatever position you get, whatever partition index you get, minus 1. That is my high. Now I'll again recursively call quick sort on the same array. Now low for the right partition is whatever partition index plus 1. So whatever position you get plus 1, high would be as it is. But it's not that keep applying this, keep partitioning and recursively calling this. You have to here check the condition. If low is less than high, then only we do this thing. If low less than high, then only we call partition again recursively call. When this condition becomes something like this, only one you can say node we have, only one element we have or 0 element we have, because in this partition we don't have anything. So what we pass in this case? In this case, when we call, the what would be passed? It's like 0, 1 and 2. So low would be passed 2 plus 1. Partition index is this, that is 3. And high would be for this, low and high for this index, high is 2. So low is 3, high is 2. Low is less than high? No. No need to call the method. No need to call partition and all. So if low is less than high, then only we call. Now define this quick. This is really important. Now define this partition method. This partitioning is the core, you can say the heart or the brain for this quick sort. Let's write down. It will return an int. So int partition. It's really simple. Whatever we have done, the steps, same we will write. So what we have? Array, then low and high. 3 arguments, 3 low and high. Now partition this. So to move, we need 2 pointers, 1 plus plus 1 minus minus. So I'll just assign int I is equal to whatever the low and int j is equal to whatever the high. Or you can take start, end, or any other pointer. It's up to you. And we take a pivot element also. Int pivot, just a variable name, whatever that ARR at low, that is the pivot element right now. We know because low is the first, at low we have the first element for that partition. So the first element I'm considering pivot element. Okay. Now what we have done? What we have done? Pivot element we have considered at first, it was 6. Then we keep comparing this side and this side. So how to write down this? We keep comparing, but two conditions. I while I is less than equal to high, and this ARR of I, the element at I, is less than same equal to pivot element. Till then we do I plus plus. I hope you are getting this condition. Same we are checking I less than equal to I. Why two condition? This condition I guess you got. We check whatever the element at ith index, whatever element at ith index, it's less than, see, it's 6 is less than equal to whatever the pivot element. If yes, then we only do plus plus. If no, then stop. So one condition is same. Whatever the element is less than equal to pivot, then only we move. Because I want the equal element of also on the left side. That's why I'm writing it equal to. But second condition is also there. One case I have discussed, I guess in this case, when I becomes greater than high, it's not that keep moving and keep checking. It will give you out of bound exception, index out of bound. Then also you need to stop. So once I is less than equal to high, then only we keep moving. So I less than equal to high and this, then only we do I plus plus. This condition is really important. Don't miss it. Next, for j, let's write down while j is, when we move j this side. So two conditions same. J is greater than equal to low, and it's not that j becomes -1 and then we still keep moving further. No, then stop. So j is greater than equal to low and whatever element at jth index, if it's greater than pivot, keep moving this side. So keep doing j minus minus. Yes. After that, once we stop, somewhere this condition becomes false, we stop. Somewhere this condition becomes false, we stop. Then we swap I and j, whatever element at I and j. But it's not that directly we swap. We check first. If I is less than j, then only we swap whatever element at I, whatever element at j. We swap these two elements. I'm just passing the index. So we have done definition of the swap function many times, passing to index and have to swap. So we swap these two elements, whatever at ith and jth index. Now we don't stop. Still, here at first, we have swapped what? I guess at first I was here and this was here. So we swapped this with this. But we still keep going this side and this side. Again. Right? So again we do the same process. We keep checking this element. If it's less than equal to this, keep going, like this. Again, find out. So we keep repeating this, these three steps. Keep repeating until I is less than j, or until low is, low is not low, I is less than j, because we are, you can say, increasing or modifying I and j, not low and high. So you have to keep these three things in a while loop. While my I is less than j, till then I keep repeating these three steps. Once my I crossed j, stop. Yes. And after that, after stopping, means we got the correct location for pivot element. What is that correct location? Wherever your jth index is. So we swap these two elements. So now we again call swap whatever at low. At low index, because at low index, whatever that is my pivot element. So at that index, whatever the element with j, at jth index, whatever the element, because the j is the correct location, we know, correct position. At the end, j was here. So this was the correct location for this 6. So we swap this with this. This is at low index and this is at jth location. We swap this with this, and at last, obviously, it is returning something. What? The index, partition index, that is j. J is the partition index. Return j. That's it. I guess it's not tough. If you get the logic, you can easily write down this thing. And that's it. It will work. Fine. Okay. Now let's analyze time complexity. So I'll discuss few cases for this. Let's analyze this. Analysis of quick sort. What do you think? If array is already sorted, then what time complexity here you will get? In this case, in worst, in best, in average, I'll discuss all the cases. The array is already sorted. Suppose I have 10, 20, 25, 30, 35, 40, something like this. Array is already sorted in ascending order and you have to sort it in again ascending order. What do you think? How you do? Same process. This is my low, this is again my high, and this is my I. I'll take 2 pointer. This is j. This is, I'll consider my pivot element. So pivot element with 6. Sorry, 10. I less than equal to high, yes, and check the element 10. Less than equal to 10. Pivot is 10. Yes, keep moving. So my I is here. 20. Is this less than equal to 10? No. Stop. This is greater. So stop here. I is here. Now j. J is 10. So j is, here we have 40. Is this 40 greater than pivot element? Yes. Move this side. J is here. 35 greater than 10? Yes. Move. J is here. Now 30 greater than 10? Yes. Move. J is here. You have to find out first smaller element than pivot. 20. Now J is here. 25 greater than 10? Yes. Move. J is here. 20 greater than 10? Yes. Move. J is here. So I is here. J is here. 10 greater than 10? No. Stop. It's not greater than 10. It's equal. So stop. Now do you swap I and j? No. We swap only when I less than j. I is not less than j. I crossed this. So I is basically 0, 1, 2, 3, 4, 5. I is 1, j is 0. So we don't swap. If we don't swap, stop. While I less than j, we keep moving this thing. Otherwise, after the while loop, we have swap pivot element with this, whatever at jth index we have. But at jth index, we have 10 only. And pivot is also 10. So we swap pivot with itself. So after swapping, it becomes itself 10, 20, 25, 30, 35, and 40. So it's like we have find out the correct position for 10. This is the partition index. This is one partition, this is second partition, but there is nothing on the left. So we don't call anything. Again, for right partition, we call again same thing. So for the right partition, there is something like this. Now we call again quick sort for this, partition for this. So this is my pivot element. I'll consider this. Same I is here, j is here. Again, do what? Is element at ith index less than equal to pivot? Pivot is also 20, na? Pivot is 20 in this case. Is this less than equal to 20? Yes, move. So I is here. Is 25 less than equal to 20? No, stop. Now go for j. J, 40. 40 greater than pivot element? Yes, move. 35 greater than pivot element? Yes, move. 30 greater than pivot element? 20? Yes, move. 25 greater than pivot element? Yes, move. Is 20 greater than 20 pivot element? No, stop. Again, but still we crossed. I is not less than j, so we don't swap these two. We find out the correct position for my pivot element. We swap this, but it will swap with itself. So after swapping arrays as it is 25, 30, 35. I hope you are getting my point. This is now my partition index because j is here. Now again, at this side there is nothing. At this side in this partition we have element, right? So what you are doing, even if the array is already sorted, but Yeah, obviously we have chosen this pivot element. So you have to do the same process for all the elements, for all the partitions. Even if in the first partition, here we were comparing n elements. Because we are moving I from here to here, j from here to here. Almost all the elements, n elements, we are doing comparison, n comparisons. In second case, here they are nothing. Here we have n minus 1 element. So again, we are doing n minus 1 comparison. We are moving this to this to this. Although in I, we just do one comparison, but for j, we move this with this, compare this with this with this with this, and this with this. N minus 1 comparison to move j from here to here. Next time, obviously, my partition is this, so I'll call for this only. Same, I will do only one comparison, but for j, we have to move till here to here. So n minus 2 comparison. Like this, we keep moving. Every time you get the partition index here at the very first, at the end, I mean, at the start only. So like this, we keep moving. Number of number of comparison. Next time, n minus 3 elements until then 2, then 1 element, like this. So if I again, you can say, combine all the total comparison, because to find out time complexity, we have to combine the total number of comparison. So just add all the comparisons. So it's from 1, like 1 plus 2 plus 3 plus up to like n n comparison. We consider n are the elements. So total comparison are this. We know what is the formula for this unnatural number n into, I think, n plus 1 divided by 2. So it's n square, right? When you solve this, you get something, but we get the we in bigger notation, we write down the highest polynomial or highest degree. It's n square. So that is the worst case. That is the worst case time complexity. Worst case time complexity in worst case. For quick sort, it's n square. Yes, it's n square. When the array is already ascending order. And even if array is already in descending order, still you will get time complexity n square. Now you have to find this out. Take an array which is in descending order and apply the same process. After 2-3 steps, you will get to know that always you get the partition either at this end or this end when the array is in descending order. So at first time you compare n elements and n comparison, then n minus 1, then n minus 2, n minus 3, and like this. So same, when you add, you ultimately will end up with this time complexity in quick sort. So the data is already sorted, but it is not taking advantage of that data. It's n square. Even it's you can say you can say that in that case, if array is random, not sorted, in that case it's good, n log n. I'll show you that how n log n. But it's increasing, it's n square, so it's not adaptive. Very first is, I guess, clear to you. Quick sort is not adaptive. It's not stable as well, right? Because if same elements we have, so relative ordering will be changed at the last. Okay, so it's not stable as well. Now let's discuss next case. In worst case, that is n square. But what about uh, best case time complexity? Now suppose I have some array. I have an array. Like here we were having some random array, not sorted or almost sorted. So we get the partition index here, almost in the middle, almost in the middle. So the best case is every time you get the partition almost in the middle. Not sure, but almost. That is the best case. So at first time you compare n elements. Yes, n elements. So partition is here. Now I'll call for this and for this. But here we have almost n by 2 elements, n by 2 elements. Right? So at every level, if I write at first n elements, then at next level we have two partition, n by 2, n by 2. Elements are n by 2, n by 2. Again for this, I get almost partition in the middle. So we divided this in n by 4, n by 4. Next time we'll call for n by 4, n by 4. So it's n by 4 for n by 4. Same for this partition also, n by 4, n by 4. Like this we keep moving till at last we left with only one element, we stop. Like this we do. This is the best case. Okay. So at this level, at first, how many comparison you need? At most n. We keep moving this with this, somewhat like. So we compare every element. So every element with the pivot element. So n comparison. N. Number of comparison I'm writing for every level. Now it comes at the next level. Now at the next level, obviously we are having two partitions. So we are doing for this and this also. Almost n by 2, n by 2. So it's almost like you can say n minus 1 kind of thing. Or if we do total, then it's n. Only one element we remove, that is already sorted. You can say n minus 1 or you can write it n itself. For the next, for the next level, if we combine this, so combinedly total number of comparison would be almost n. Almost n. Not exactly n, but almost n. Right? Like this. For the last also, we can say almost n comparison. Almost n. Okay. So it's like for every level, number of comparison are almost n. It's like a tree. How many levels are there? It's like a tree, like binary tree or that complete tree. So the height is, we know, every time at every level we are divided by 2, divided by 2, divided by 2, like this till 1. So height is, in this case, we know it's log n and base 2. Height would be, the recursive tree would be, height would be log n base 2. So height is this, or number of levels are this, and at every level we are comparing how many comparison? N. So total number of comparison are n log n. So that's why the time complexity in best case is n log n. In worst case, n square. In average case also, it's n log n. So that is why quick sort is a little bit better than the previous, because time complexity is reduced to n log n. But yeah, still in worst case, it's n square. Okay. And best cases when the data is already sorted either in ascending or descending order. Then you always get the partition at one end, either this end or this end. So that this is the worst case, n square. Best cases, you get almost the partition in the middle. Any random data we have, not sorted, but partition is almost in the middle. So that is n log n time complexity you will get in the best case. Yeah, you can optimize this also. Even in this case also, n square. I just pick any random as a pivot. I don't take this or this as a pivot. I take any random or the median element as a pivot. Maybe in that case, we can optimize this time complexity to somewhat. It's n log n, maybe not n square. It depends. Sometimes the choosing of the pivot element also, uh, you can say, important. Sometimes want to reduce in some cases time complexity when you're dealing with this ascending or descending array or already sorted data. Then rather than picking pivot this or this, take any middle element as or random element as pivot and apply the process. Okay. So that's how quick sort work. So we have analyzed this. Now if you want, you can choose pivot element last and you can apply the same process. So here we have chosen pivot element as the first. So you can choose the last and apply the same process, or you can choose the median element and apply the same process. It's up to you. There can be many ways to solve you can say solve quick sort. It's not only one way that always choose pivot as the first element as pivot element. And I have told you it is not stable. So if I write down few more properties of this time complexity we have seen, it's not stable. For the same data, relative ordering will change after sorting. It's not adaptive also. It will not take advantage of already sorted array, even if version the time complexity. Although if you change the pivot, you can say position, maybe you get better time complexity. Third, yes. Now space complexity for this. Space complexity. Are you taking any extra thing here? Although we are doing in the within the same array itself, but the thing is when you are following recursive approach, then we need the call stack. And in best case, yeah, call stack is same like according to the height of the tree. Then that is log n. But in worst case, it can be n. But in the worst case, because worst case is this, right? And then n minus 1 comparison, n minus 2 comparison. So in this case, what we are doing at very first, the tree would be something like this. We have n element, then we got this. So in the left side, there is nothing. On the right partition, we have n minus 1 element. Then again, left side, there is nothing. Here we have n minus 2 element. On the left side, there is nothing. Then again, like this, like this. 2, then left side, there is nothing. There is only 1. So the tree is degenerated, skewed kind of thing. So the height is n itself in this. So in worst case, space complexity may be up to n, order of n. It depends on the type of data you have, right? But in best case, it's log n. So it is for when you are calling, when you are writing recursion. For recursion. Otherwise, it's in place. When you call iterative approach, no recursion. So no recursion stack you need. So there is no extra array or something like we are taking. Within the same array itself, we are swapping and some kind of thing we are doing. So swapping and all. So it's in place. If someone asks, it's in place or not? Yes, it's in place. Right? Okay. So now let's try to, now you just pause the video and try to run this program. So let's create a new Java class for quicksort. Here we will take an array, same array we take quicksort, this. Or you can create a new class quicksort main, and there you will call quicksort separately. It's always a good idea, like create main separate class and logic, whatever logic you write, implementation kind of thing, that is a different class. But here I'm writing in the same class itself. So I have an array. Now I'll call quicksort. Quicksort. I'm passing whatever array I have. I'll pass low. Low is right now 0. And high is whatever array length minus 1 that I'll pass. That is my high. Yes. Now here, let's make it static because I haven't created any object to call this method. So make it static. Void quicksort. Here we have 3 parameters. One is low and one is high. Now, in quicksort, we partition, but first we check if my low is less than high, then only we call partition and recursively call quicksort. Otherwise, we don't call. If low is less than high, then only. So we call here partition method. There I'll pass array, whatever low I have, and whatever high, lower bound and upper bound. Whatever it will return, that would be, suppose I have in position or partition index. Let's name it partition index. Any name you can take. It should be descriptive. Now I got partition index. Now I have two index. Now I'll call again recursively quicksort for the left partition. So there I'll pass my array. Low would be as it is for that, and high would be whatever partition index minus 1. Then for the right again call, array would be as it is. Low would be now partition index plus 1, and high would be as it is. That's it. Now define this partition method. Let's define. So make it static, int partition, and we have to take same 3 parameters because we are passing 3 arguments. Same variable name I'm taking, same parameter name here, low and high. Different also you can take, it's up to you. Okay, now let's code this. This is really important. Partition. Okay. At first, let's take my pivot is equal to whatever at low we have index, the first element that I will consider pivot element. Now I'll take 2 pointer to move. I is equal to low and I have j is equal to high. Very first, when I is less than j, then we keep repeating the steps. So we keep checking while I is less than equal to high and and whatever at ith index, the data is less than equal to my pivot element. Then we keep moving forward, I plus plus. Next, while my j is greater than equal to 0 or whatever low we have, low, and whatever index at jth I have is greater than pivot element, then we keep moving. I mean, keep decreasing this j. Once we stop I and j, once we stop, then we check. You have to swap I and j. If I less than j, then only we swap. Then only we swap from this array whatever at ith and jth index the data. Yes. So yes, we are done. After this while loop, after closing of this while loop, now we got the correct position for my pivot element. Now we call swap again. Sorry, it's swap from this array. Now I will swap whatever at my pivot element is at index low, and the correct position is j, wherever the jth index right now, that j. And at last I'll simply return j. Simple. But now, yeah, you have to define this swap also. Let's define. It will not return anything, so void swap. I'll passing my array also, array int I and int j. See, remember, we don't here pass simple the array elements whatever at ith and jth index, because it will be called by, we'll pass this by copy, and the local copy would be updated, not the actual array. This problem we have faced in the previous lecture also, when we were discussing, say, I guess, insertion sort. I guess you got it. So we are passing the index. Now actually we are fetching the data and we are swapping. So int temp, at first I'll take whatever at ith index, then whatever at ith index, there I'll store whatever at jth index, and then whatever at jth index, there I'll store whatever I have in my temp. Sorry, it's temp. That's it. That's how I do swap. So now we are done. Yes. Okay, non-static method. You have to make it static to call it static, because we are call this is a static method. Within this, we can't call any non-static method. So swap is done. Now, if I run that, it will not print anything. So you have to print the array. So either you can loop, or you can use a loop to print the array, or you can directly write down arrays dot toString, this method, and just print array. But to call this method, we have to include this java.util.arrays, this class. Don't forget, you have to import this package, this class, from this java.util package. Now simply run this and see. It will give you 1, 1, 4, 5, 6, 10 sorted data. So yeah, 1, 1, 4, 5, 6, 10. We got it. Now if I pass like this, what will happen? Let's see. Empty array we have. Okay. I have only one element. Then also let's run this. So obviously that's already sorted. So only one element it will give you. 1. So this is quick sort. I guess it's not that much tough. If you get the logic, you can easily write down yourself this partition. This is really important, the partition logic. This is not that much tough, because recursively only we are calling partition, and recursively we are calling again quick sort for left and right partition. That's it. If you want to dry run this with recursion, we know I have discussed already how to dry run when discussing recursion in a program. So you can dry run this yourself by pushing the stack frame for every recursion call. And ultimately you will get to know the space complexity also. How many frames there would be there in the call stack. So the time complexity you can analyze with that. So now we are done with quick sort. In the next lecture, we'll see what is merge sort. So in the next lecture, till then, bye bye. Take care.